Welcome everyone. In this video we will prove Euler's very famous formula that states that if you have e raised to the power of I theta, this is equal to cosine of theta plus I sine of theta. Here theta is measured in radians and I is defined as the square root of -1. So how can we carry out this proof, which, as I said, is Euler's formula? Euler's formula. I think it is also called Euler's identity or something like that. But enough of the names. How can we prove this statement? To start my proof, I want to consider the quotient e raised to the power of I theta divided by cosine of theta plus I sine of theta. So I simply divided both sides of our statement, of our formula here, by what is on the right side. If Euler's formula is correct, this should equal 1. So our question is this equal to 1? Well, we will see about that. We will find that out. And now we will take a derivative. You might be wondering, why would we take a derivative? And at the end of our derivation, at the end of taking the derivative, you will understand why. And I hope it will be a great tool that you can use in other questions or other proofs, because it's a really interesting idea. So how can we take the derivative of this quotient? So what is the theta of this thing? And to have enough space, I am going to erase the 1 here. And let's see, what is the derivative? Well, to take the derivative of a quotient, we will use the quotient rule, which I proved in the last video. So if you haven't seen that one, please do so. And here we go. To take the derivative of a quotient, as I proved, you first take the derivative of what is in the denominator. So what is the theta of e raised to the power of I theta? Well, let's work on it here in red. So the theta of e raised to the power of I theta can be represented as, using the chain rule, as like this: the I theta and like that, e raised to the power of I theta times the theta of I theta. This is simply using the power rule. I mean, not the power rule, the chain rule, excuse me. So if you have this thing right here, so you can think of it as I theta being x in both cases. So what is the derivative of e to the power of x with respect to x? It is just e to the power of x, and our x in this case is I raised to the power of I theta, times, here we have I theta with respect to theta, which is just I. So the first derivative, the derivative of the quotient, is I times e raised to the power of I theta, times, we will multiply it with the the denominator, and I will erase this calculation so that we have enough space. So we multiply it with what is on the denominator. I keep saying this wrong. I'm sorry about that. We got this. And we put a minus. Then we take the derivative of what is in the denominator. What is the derivative of cosine of theta with respect to theta? It is negative sine of theta, as I proved in a video that was a long time ago, plus the derivative of sine of theta is cosine of theta. We also have I here, cosine of theta. So this was the derivative of the denominator. I said it right this time. And now we write the numerator. We multiply it with the numerator. So e raised to the power of I theta. This is all divided by what is the square of what is in the denominator. So we have cosine of theta plus I sine of theta squared. Great. Let's see what this derivative is equal to. So if we distribute this I that we have here inside the parentheses, if we distribute it to the parentheses, let's see what we get. We still have e raised to the power of I theta. Then we have inside the parentheses I cosine of theta. Then we have plus I squared sine of theta. If you remember our definition of I that we made here, you know that I squared will be negative 1. So we will just have negative sine of theta. Then a minus, we have e raised to the power of I theta. Then inside we have, if we arrange the order, it doesn't matter in case of a addition, so we can do that. We have I cosine of theta minus sine of theta. And now we have our denominator as cosine of theta plus I sine of theta all squared. Well, you should be very excited now because look at what we have on the numerator. We have this product here and we have the same product here. We have something minus itself. This should be equal to 0 then. Well, that's interesting. This is telling us that if we take the derivative of our quotient, which was here, we get 0. Well, okay, it's cool, but what does it mean that we get a derivative of 0? It means that since derivative represents the change, if we have a derivative that is equal to 0, our function does not change. So, if we were to graph our quotient, we would get a horizontal line, which makes sense because the slope of a horizontal line is 0, which means that this is the key point of our proof. Our quotient of, and I'm going to write it here, e raised to the power of I theta divided by cosine of theta plus I sine of theta. This quotient should equal a constant. It should equal a number. It might be 10, it might be negative 11, it might be pi, it might be e, but it should be a constant because we showed that the derivative is equal to 0. There is no change, so it should be a constant. This is incredibly interesting, I think. But how can we figure out this constant? I mean, what is k? Well, let's just substitute 0 for theta, for example. We could substitute any other angle. For example, we could substitute pi over 2, pi divided by 4, pi divided by 16, but 0 will make the calculations the easiest. So let's substitute 0. And let's do that on a new page. So we have e raised to the power of I, this time 0 instead of theta. Then we have cosine of 0 plus I sine of 0. And this is, as we discussed, should be equal to a constant, which we called k. K here is a constant. Well, what is e raised to the power of I times 0? I times 0 will give us 0. E raised to the power of 0 is simply 1. Divided by cosine of 0 is 1 plus we have I times sine of 0 is 0. So we have I times 0, which will give us 0. So we have 1 divided by 1. This is equal to 1. And it is also equal to k. Well, how about that? We proved that k is equal to 1. This is great. So if we return to the general formula that we got here, the one in blue and inside the red box, then we can say that e raised to the power of I theta divided by cosine of theta plus I sine of theta is equal to k, we just argued, and we just proved that k is equal to 1. So if we multiply both sides with cosine of theta plus I sine of theta, we will of course get e raised to the power of I theta is equal to cosine of theta plus I sine of theta. And that is it. We proved Euler's formula. I hope you found this proof interesting, and I think there's a lesson to take here, a very important tool that we can use in other derivations, for example, or in other problems. This idea, taking the derivative and then seeing that it is equal to 0, is a great way to prove that some function, some expression is a constant. Okay, I hope that at least this sticks with you for the rest of your math career. Also, just a quick note, this thing cosine of theta plus I sine of theta, well, it is kind of long thing. It is a long thing to say all the time. So we sometimes abbreviate it as cis theta. Here, C comes from cosine, I comes from I, S comes from sine, and theta comes from theta. So you can also abbreviate cosine of theta plus I sine of theta as cis theta. This is just a definition, a shorthand of writing it, and I actually like this abbreviation. Anyways, I hope you found this video interesting and helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.